Hi everyone, I'm Nandavardhan and my teammates are Deepak, Krishna and Saketh. Today we'll be presenting our findings in our project in the course of algorithms. The title of our project is Comprehensive Analysis of String Matching Algorithms. In today's world, where the computers form the essence of most tasks, knowingly or unknowingly, we rely on different string matching algorithms, where it is as simple as using find in a Word document or performing search using the Google search engine to find relevant web pages. Other such critical applications range from applications such as spell checkers, spam filters, plagiarism detection, or intrusion detection systems. Due to the huge variety of tasks, it led to the invention or discovery of a wide variety of string matching algorithms over the past decade. The traditional string matching algorithms work by comparing strings at a character level, neglecting contextual and semantic information, while the modern NLP algorithms perform contextual string matching, which is extremely useful in some applications. The growth in the usage of search engines or spam filters have made the application developers develop very high reliable resources, and hence the need for better and more efficient string matching algorithms still keeps the research going on. Through this project, we intend to analyze several string matching algorithms to understand how these real world problems are being solved. By the end of this presentation, we would like to have answered the following question. Suppose we are given a string and want to find all other strings that match with it from a set of documents. How do we find the strings that match or are the closest match? If we have few documents with limited words, then it would be an easy task. But consider a scenario of having documents where we have about 100 documents, then it would be very difficult to get the similarities using the traditional approach. So in this case, we should try to analyze different string matching algorithms and use the optimized one. So in this presentation, we'll be going over four such algorithms, namely the shifter algorithm, Seller's algorithm, the engram-based algorithm, and the BERT algorithm. Let's start off with the shifter algorithm. The shifter algorithm, also known as the bit API algorithm, was proposed in the previous decade. It was one of the first string matching algorithms that was proposed that uses bitwise operations to achieve both high performance and efficiency. For the case of exact string matching, the bit API algorithm encodes the pattern into a bit matrix and uses it to search for the pattern in given words. This concept has also been extended to work for fuzzy string matching. In fuzzy string matching, since we will be looking at approximate or close matches with the pattern, we're also using a distance metric called the Levenshtein distance. Although the Hamming distance was used originally, it was later shifted to the Levenshtein distance. Now, this distance metric that's employed, it quantifies how close a word is with a given pattern. Levenshtein distance, simply put, is the total minimum number of operations it would take to change one word into another. So if the given pattern and a word are at most at a distance d from each other, then we consider them to be similar or the same word. Now, the shifter algorithm, it has mainly two stages in the algorithm, namely the pre-processing stage and the scanning stage. In the pre-processing stage, we compute three tables, the shift, hash, and prefix table. Although we're computing three tables and it's a little bit of computation, when we are working with a large number of documents and a huge number of patterns, it's very efficient during the scanning stage, such that the overall runtime complexity is efficient. So we use the three tables to determine what substrings to skip over and to what paths to check a pattern against. And during this scanning stage, we iterate over all possible substrings in the text and we compare it with the relevant patterns using some uh, predefined algorithms. Yeah. This algorithm runs in linear time as a function of the length of text. Now my teammate Saketh will take over and explain the Seller's algorithm.
Hi everyone, my name is Saketh. Now I'm going to discuss about Sarlas algorithm. Sarlas algorithm is an approximate string matching algorithm which uses DP technique to give similarity between two strings. It was developed by Sarlas in 1974 The idea behind is to minimize the edit distance between the two strings. The algorithm basically uses a Levenstein distance as the edit distance, which is a string metric to calculate the difference between the sequences or string. It is just a number that tells you how different two strings are. The higher the number, the more different the two strings will be. The first part of the Sellers algorithm is to find the Levenstein distance between the strings which we are comparing. And the next part would be to use the Sellers algorithm to complete the 2D matrix and fill the minimum edit distance between the given row and column and get the similarities between the two strings. The Sellers algorithm can be implemented in many ways. One such way is to use the Python package known as Fuzzy Fuzzy. It uses 11-strand distance to calculate the differences between the sequences and get the similarities between them. The ratio method in the fuzz is used to give the similarity between the strings. So if the first string has length p and the second string has length q, and if p is greater than q, it takes approximately big O of p square q time to compute the algorithm. The next algorithm will be explained by my teammate Deepak. Thank you.
Hello everyone. The next algorithm we'll be covering is n-grams algorithm. It's an NLP based technique. So n-gram basically is a sequence of n words, where a 2-gram is a 2-word sequence and a 3-gram is a 3-word sequence, and so on. So n-gram is a probabilistic model which is usually trained on a corpus of text. So n-gram has wide usage in many NLP applications like speech recognition, machine translation, and predicting text. We basically calculate the probabilities and count the frequency of word sequences in the corpus text. N-grams is really helpful in sequential analysis because an n-gram model predicts the occurrence of a word based on n-1 previous words. So here we'll be answering the question, how far back in history of a sequence of words should we go to predict the next word? For example, a bigram model predicts the occurrence of a word given only its previous word. A trigram needs 2 previous words to predict the next word, and so on. So using n-grams algorithm, the similarity between two strings can be calculated using the below formula. So the similarity is given by a number of matched bigrams by the total number of bigrams. If you're using trigrams, it would be the number of matched trigrams by the total number of trigrams. And the distance would be given by computing 1 minus the similarity we get. The time complexity of n-grams algorithm is order of m into n, where m and n are the lengths of two strings we are comparing. N-gram algorithm has many advantages over the traditional edit distance approaches. One main advantage is that n-gram approach takes significantly less disk space. The editing distance metrics require storing an entire dictionary in memory, which is not the case with n-gram algorithm. N-gram approach optimizes memory by creating a dictionary of n-grams. So to compute n-gram representations, two approaches are typically used. One which is quite slower, which is based on Markov models, and the other one which is significantly faster, which uses a method based on set comparison. So the next NLP technique we'll be covering today is the BERT algorithm, and this will be covered by my teammate Krishna.
Hi, my name is Krishna Mallik. So I'm going to cover BERT algorithm that we have used to compare the strings. So BERT is a bidirectional encoder representations for transformers. This is a neural network based algorithm. So as the name suggests, BERT has two parts in it. One is the encoder and the other is the decoder. As we are focusing on the use case of string matching, BERT performs the encoding part to understand the context of sentences by the encoding from the encoder side. So we just focus on the encoder side of BERT. So as you can see here, the BERT has three main steps in its processing. One is encoding the sentence, understanding the context by adding the attention mask to the vectors, then computing similarity based on distance metric. So the encoding sentences develops tense vectors, which are then processed towards the attention mask area, where the attention is added to the BERT algorithm, the encoder output. So as I am stressing more on attention mask, the main layer in BERT is the attention layer, which adds weight to the encoded words. Those words are then mapped to the output, and as the weight increases, the context and importance of those words increase. when word A is mapped with word B on the output side, when A has more weightage, it means that A is more equal to B on the output side. We can also say they both are similar in meaning. So that's how the context is learned by BERT algorithm. And these words are processed one by one with by considering all the words in the sentences. So it takes big O of d into n square time. D is the dimension of encoding. As the word sentences go into the word first to get encoded, those encodings are done in d dimensions. Each dimension is corresponding to each sentence and word. So those words are now to be compared after giving the attention to those. So as we compare the n words with other n words, it is an n square time complexity over there. So that's how big O of d into n square time is taken by BERT algorithm. So how BERT got introduced to the society is by Google R&D team. The main use case of BERT string similarity is Google search engine. So before BERT in Google search engine, whenever there is a sentence which is not properly framed and does not have all the words in it to get matched for appropriate results, it used to give shabby results to up to an extent that it used to understand only some part of the question, and it used to give one-on-one matchings from those words and give results for the user. But when BERT is introduced to Google search engine, however the sentence is written, however they type the sentence, the BERT understands the context of those sentences and then provide most accurate results that is possible by Google search engine. So that's how BERT has changed Google and its search engine optimization. So from all the four algorithms, we would want to analyze something to answer our question in the next slide. So as you can see, all the four algorithms have different purposes, and they do not have a single approach where they all excel or fail in one thing or the other. We cannot say that there is a superior algorithm in here of the four. They all achieve good results in different use cases. For example, we have two types of algorithms that we have taken to compare: the NLP based algorithms and the dynamic programming based algorithms. The NLP based algorithms understand the context and provide a similarity score by taking this edge of not just by comparing it by distance metrics. That is being done by the dynamic programming techniques such as the Sellers and Shift or algorithms. They just go by the distance between the sentences and give the similarity. So to conclude, we would want to say that the use case that we were looking for is to compare large documents and see the similarity between them. So as we are going forward using these algorithms for large documents, BERT is an optimal algorithm for us in this use case. As BERT does not only compare on word-to-word basis, but also understands the context and gives us appropriate results between all the documents. So this is how we would get benefited by understanding the context of those documents and take some of them after the BERT gives us the similarity scores. And also, as it is implemented by neural networks, it can process huge documents easier compared to the other algorithms. So that's how we would want to conclude by using BERT for our question. We would also want to take the time to tell about the future work which can be done on this project, and we would definitely do that if time permits. So as we have gotten only 2 weeks of time frame, we couldn't explore a lot of other algorithms that perform string matching, and also in the future we would want to implement the algorithms in MapReduce environment, which is a parallel programming paradigm for large data analysis. And also we would want to continue our research on this topic and work on algorithms like RabbinCarp and Boyle more. We also intend to apply this algorithms on real world data sets and see how they perform. and look for better algorithms and get updated on those as well. Thank you so much.